Our next presentation is going to be from Jay Rogers. He is the CEO and co-founder of LM Industries, and he's going to talk about building a digital OEM. And backstage, I was talking to him, and I was just asking him about his life. He said he served 9 years as a U.S. Marine. So, hoorah! Let's give him a big round of applause.
Thanks, Tom. Thank you, good afternoon, and thank you for sharing the last bit of time between going out for a beer and enjoying the Phoenix heat. So we're going to talk a little bit for what it's worth. Digital original equipment manufacturer can mean a lot of things, and I hope that during the time that we have right now, I'm going to be able to give you a vision from where we started to where we are today. In the last decade, almost every product that we know of, that we use and touch on a daily basis, has been disrupted by digital. The top line that you see, you recognize for all the products that we knew growing up in homes or working with, and that still exist in some businesses today. Underneath them, the products that look a lot like them, as we all know, have many different functions. But these are the products that have been disrupted by digital, and I would say that except for these, we've seen the same trend. When you get in a Ford today, or you get in a Tesla, or you get in many of these other vehicles, you find that the usage of it is still very much about getting from point A to point B. It's not like a camera that you had before that now is also your internet-enabled device and is the place where you check something and touch it 2,500 times a day. You touch your vehicle about as many times a day as you did 20 years ago. And so when you think about how to disrupt these products, it gets right down to the soul of what's happening in manufacturing, something you can touch. So I want to start this conversation with a view of the end. And Shelby, if you would, we'll play this video.
This is the end. The end of the assembly line. The end of the showroom floor. The end of the smooth-talking salesman. The hard sell. The soft sell. The oversized inflatable gorillas and overinflated inventory that absolutely must go. This is the end of the junkyard full of old cars leaching chemicals into the ground. Born from the concept of cradle-to-cradle manufacturing, printed in front of you to be the exact car you want. Melted, deconstructed, and rebuilt to be the next car you need. This is where vehicle manufacturing as we know it comes to an end. And where vehicle manufacturing as it should be begins.
Starting at the end gives you a really good idea of what it was like to come along this journey. In 2004 and 2005, I was a Marine patrolling the lower 250 miles of Iraq. And during that deployment, 2 of my friends were killed, one in a Humvee in a frontal ambush, and the other one in a CH-46 helicopter that was shot down, flipped over, and he drowned in it. And during that deployment, I was really thinking hard about whether I was going to share the same fate or whether I was going to come home and do the next thing that came along in my life. And I was reading a book at the time, and it was written by a brilliant guy named Amory Lovins, who was talking about using epoxy composites to be able to make lightweight sheet material. And so that was known as FiberForge at the time. The business doesn't exist in the same form that it did before, but it was inspiring for me to think about building things in a different way. And I knew that if my friends had had the opportunity to have different equipment in Iraq, that we would have had a different outcome for their lives, certainly. And that inspired me to start this business. But I started by going back to the drawing board. Many of the fundamentals of manufacturing, starting with that video in the end, were things that I was just imagining at the time. I wanted to be able to make products, make big products, make vehicles digitally so that we could accept new technology into them. At the time, I was thinking about things like armor and drivetrain and Blue Force trackers and other things like that. But the point being is that it was so difficult to be able to stamp steel and to be able to make tooling that it was difficult to imagine how you could reduce the cost and reduce the time to develop a vehicle in order to be able to onboard that new technology. So we went back to the drawing board, and I was sitting there with a piece of paper in my Quonset hut south of Baghdad, thinking about how I was going to build this business. And it started with these 2 elements. The first one, at the end, the microfactory, I imagined as something like carving a clay model, not by hand, but doing it by a CNC device. I had used plasma cutters before. Water jets weren't around for something for me to use, but I was imagining something that could move fast and work on a structural material. And that was the concept of putting it together in a microfactory where you could have one machine that worked on digital instructions, or you could have 20, and it didn't cost you any more if you wanted to add them, just the CapEx of doing it, but there wasn't any economy of scale that you would get. And so then on the other side came about a year later. As I really began to dig in and write the business plan for the business, I thought, what if I am right? What if we could discover a digital microfactory that really could work from concept to production very quickly? I wasn't sure where all the ideas would come from. And by ideas, what I mean is not just the designs, but where would the technologies come from that would be the new pieces of armor or pieces of gear that you would hang on. And one of my advisors said, you know, you should start a global community. I met this t-shirt company that was asking their customers what kind of t-shirt did they want to buy. And we did. So today, LM Industries is made up of two parts, Launchforth on the left and Local Motors on the right. Launchforth designs it with our community. Local Motors makes it and takes it to market. Launchforth designs it. Local Motors makes it and takes it to market. And I want to talk about what that process means. When Launchforth goes to market with our customers, when they talk about designing something, they're employing this principle of co-creation. And really what it is it's a collaborative engagement between a global community of people that we steward, that we've built over the last 12 years, and with experts that we recruit actively to bring knowledge to the process of co-creation, and our own team that's going to end up being responsible for prototyping and micromanufacturing these pieces of gear. That's what co-creation is. Microfactories are a little bit different. They're expeditionary boxes that are driven by digital, all the way through. We think of DDM as something that's in our soul, direct digital manufacturing. A lot of people like to throw the word prototype at us, and it's something that we try to kick off or shrug off our back as much as possible. Direct digital manufacturing for us is the promise of what a microfactory can offer. It's something that it can take from the co-creative design and make it real in a unit of 1, a unit of 100, or a unit of 2,500. So here's where we are today. Our community, after 12 years of incredibly hard and fun work, is over 180,000 people worldwide now. That means that we can run challenges for things we've never even dreamed at the beginning of the year or the beginning of the month that we were going to work on. We've run over 100 of those challenges, and we have so many designs that are getting refined, and it's the tools and the reason why I'm here talking to you today that make this possible. In the last year, we've distributed, thanks to Siemens, 2,800 licenses of Solid Edge alone. So for a starter project, for a mainstream engineering product for those community members, there is clear uptake for these experts to be able to get better at what they're doing in a digital world. It's important for them to be able to have great tutorials, and it's important for them to be able to have peers in the community that they can look up to. So the other piece of the community that I now rely on, that we rely on in our business, but wasn't intuitive when I was first writing the business plan, is a growing labs network. So you could have ideas from your community, and you can have microfactories that can put them out, but the technology that flows into those products is often the seed of what we make. So when you think about autonomy today, autonomy is full of many different types of technologies: sensor technology, CPUs, VCUs, ECUs, GPUs, TensorFlow chips, wire harnesses, all those kinds of things. And every single vendor has an idea of what they could do that's new. And usually they're pretty scared to share it with the OEM that's currently buying their bulk product, because they know that the time to get it into market is longer than what they typically would like in order to be able to get a real test bed with customers. So we have promised something to our labs network, which is growing, to be able to get their newest technology into vehicles in a cycle where they can get feedback and decide whether they want to put more money in it or not. So we think of the whole process as going from ideation to product. And when you think about what that means, there's a simple graph that we've been able to draw, and there were versions of this that have been out for a long time, and now we feel it every time we work from Launchforth all the way through to Local Motors. The traditional cost curve, you know, it goes from really expensive development cost, amortized over very few units, and then it slopes down, if you can see my cursor here, to many units, and the development cost is amortized. When you employ direct digital manufacturing, what you're basically doing is taking this black curve and you're flattening it to the blue line, which means that suddenly you can become competitive in making fewer units at a lower cost. That's the microeconomic analysis, and I promise is the last chart that I'm going to put up, at least one that looks like that. So what it really means to us is it means that from CAD to, from challenge to initial CAD, we've proven that we can bring our community to that cycle in less than 4 months. Then we throw it across the line, and we go from CAD to MVP in another 4 months. So in 8 months, we're taking something that never existed except in the specifications of a challenge and putting it into a prototype that will be able to go on through direct digital manufacturing into a product. That's what we promise when we go after some challenge for our community. So some origins to our success today. We started with the Rally Fighter. Guinness Book of World Records calls it the world's first crowdsourced or crowd-derived vehicle. And this was a really exciting project because we had never even dreamed how much the technology would come along in a microfactory. We finally were able to access some basic technologies for mold building, panel making, tube cutting, other things like that. And we really pressured our CAD software and our CAM software as much as possible to get the Rally Fighter out. We made 100 units of it before we ceased production of the Rally Fighter, but it was the promise of what was to come. And then in 2014, we debuted the world's first 3D printed car. This was an awesome evolution because it was such a huge step forward for us to be able to run a worldwide design challenge, source this guy, telling him basically what we thought the technology could do. We had never printed a car this big before, and the first vehicle that we printed, assembled, and drove away happened live for us and for our community at the same time. And so then we went on with Airbus to build the world's first crowdsourced drone. The winner here was Russian, not Italian, not Korean, like the former two winners. And this drone really got us to where we are with Airbus today, to think about how you can succeed, fail, looking at various different modalities of flight controls, aerodynamic surfaces, serviceability, other things like that, and move a community to be able to participate with a large company like Airbus, which is good at aerostructures and good at certification, but not good at speed. So it was a great partnership to show how we could work at mobility, but move things beyond the ground. And now moving things forward to one of our latest projects, Ollie. Ollie is a low-speed cognitive EV. The world right now, if you read any technology rag, is awash with autonomous vehicles. Specifically here in Phoenix, where we have a microfactory, we have become famous for many things, not the least of which was the first human fatality this year, and maybe the first of all time with a robotic vehicle, and so that was trying to drive at level 4, level 5 capability. So it's a huge concern for many people in the world. But you know what I think the bigger concern is? The bigger concern is that we're undershooting the promise of what our compute power and what our robots can do for us in life. Taking an autonomous vehicle to the road is not about getting to someplace cheaper and faster. The mobility graph that you have today when you use your car is totally analog. You get up in the morning, you go to the same place 95% of the time, and you still have a great chance of being distracted and hurting somebody in the car when you get in it. 95% of all accidents are human engendered because we're tired, angry, distracted, or many other things that happen. Autonomous vehicles wipe that off the face of the earth, and the technology is capable right there to do it today, no argument. But beyond that, they can make it so that you never even have to get in the vehicle. They make it so that a grandmother and a grandfather can call for their grandchildren to come visit them without ever having to get in a vehicle. They can change your mobility graph entirely, and what they can really do is they can make cities more competitive again. Places where you live and work don't need as many vehicles because autonomous vehicles make it so that you can shut the street lights off. Shared mobility helps. And getting in vehicles that are smoother operating helps. But really, getting rid of the congestion and allowing all that to come together in a robotic vehicle is what really makes the difference. So Ollie was the result of one of these challenges and micromanufacturing efforts, and I'm going to come back to that in a second. I'd like to highlight this, which some of you may have seen in one of the smaller sessions that we did before, but this is really such an amazing project that we worked on. If you think about where I started in 2005 in Iraq, wanting to change military gear, and being where I am today, this is the most gratifying work I could possibly do for our business. The Marine Corps came to us, and I had the honor of hosting the Commandant of the Marine Corps and the Sergeant Major of the Marine Corps and the head of the Installation and Logistics Command for the Marines at our microfactory in Tennessee. And what they wanted to see is what could Marines do if they were given access to actually put feedback into the co-creative loop. And that's what we did. So we told them these three things: we'll co-create, we'll manage it, and we'll make it. And we started with a challenge. A modular logistics vehicle with 4 attributes that we needed to get to. The first attribute is we wanted to be able to say hackable's not a bad thing if we're going to go after personnel movement. And so Marine bases are big, and they're difficult to get around, and you're constantly carrying things that are non-standard, people and equipment, moving from A to B, and A and B move around. And so being able to move people with something that works was something they wanted. The next was administrative support. This is something we totally didn't think about. If you take a round of 5.56 ammunition or a whole pallet of 155 rounds, for those of you that don't speak militaryese, 5.56 is about that big, and 155 is about this big. But when they come in pallets, you really know it when you break this one open, because you have these huge rounds that are no longer palletized, and each one of them needs to be controlled. So if you don't fire it, or it gets wet, or other things like that happen, you don't want it to just go back in the pickup truck and go back to the base. You need to control for it. But if you have a hard time taking people and gear around, you sure as heck have a hard time doing administrative support out in the field, out in the rain, out in the sun, and that's on base. In combat, it's just as bad. You don't want to be leaving a whole half pallet of somewhat used ammunition without control on it for the enemy to pick it up. So what the Marine Corps is looking for in administrative support starts on base and it goes to the field. And then beyond that, of course, mechanical support. You want to be able to fix the gear that's out in the field, and then as you get new gear that flows in, maybe it's a transnational partner or other things like that, you want to be able to upgrade the vehicle that you have that provides mechanical support. And lastly, you have construction support. We build a lot of things. We build HESCO barriers, we build all kinds of guard posts, we build fighting positions, we build humanitarian assistance, log positions, other things like that. Forward arming and refueling points. It's an intensive environment. And so having a vehicle that could do all 4 of these things is what the Marines tasked us to do. And bottom line up front, here was the winner. Out of hundreds of entries that came in, this man designed a vehicle that the Marine Corps and a panel of judges chose for being the right direction for where we wanted to go on the digital thread. And then we threw it back into the co-creative loop, and we took what he came up with and we did a refinement challenge. And this refinement challenge came from a totally different community member half a world away that dug into the intensity of the modules that he wanted to carry around on base and built this vehicle called the HAT 2. So I want to dig in under the covers just a little bit and explain what the digital thread means to us. So when you think about it, going from co-creation through prototype all the way to product in direct digital manufacturing, these are the elements that you find. You need to be able to develop the situation, and sometimes you're doing it from scratch, like the Marine Corps started with us, and sometimes you're doing it from something that was sort of good, but needed to work better. And so bringing out that and making it transparent is what we're looking for. So I think of it as a digital innovation cycle, and what you're looking for is you're looking on the outside. If you think of these concentric circles, think about them like an onion. The orange ones get really leafy at the outside. They're porous. People give you a lot of input, and it's mainly subjective. You're getting validation for the decisions that you make. If your eyes are glassing over when you're thinking about subjective things that aren't driven by data, it's exactly that that can cause you to make good decisions before you take the technology and apply it to a solution. And so when you think about that, then you're going through and you're saying, can I identify, as we move along this thread from 1 through 9, you're thinking about, can you identify all of the pieces that are going to make this thing come together with as much simplicity so that we can hold it in a Marine's head and think about how it's going to meet all of the things that I need to do. Cost, is it going to be serviceable? Is it going to get the mission accomplished? All of those kinds of things. And it's really difficult if they can't see the end up front like we started. So in the middle of it, the harder part, the blue circle, is the digital microfactory. And that was one of the things that I think we were able to show them and crystallize, is that it's not expensive to build a digital factory. What's expensive is to make products that don't keep the warfighter safe. That's where I started in 2004, but the tools weren't available then to be able to make this happen, and today they are. So when I think about a digital supply network being dynamic and self-optimizing, it's definitely true today in 2018, and I just came in from Germany 30 minutes before I got on stage here, and I was at an AI consortium with a great deal of folks that are working in our labs network. And we're talking about the application right now of artificial intelligence to that labs network. Go all the way back to the beginning in 2005, where the idea was if you could build a digital factory, you would need many more ideas so that you could sift through them all. We're now at that stage, where now the technologies and the ideas are getting so voluminous that we need more intelligence in order to be able to sift through them so that we can proffer the right ones that we can go after and see whether it's worth spending the time with. So that's a growth of where we are in the digital supply network. And all these things surround that when you're going through. This you may have seen before. This is not our diagram, but I like putting it up because I think it shows the promise now of where we're going. Design, build, validate, and feedback. There are different kinds of feedback. Sometimes feedback is failure, meaning this whole system doesn't work, which means you have to go back to the drawing board to co-creation before you're even thinking about putting something in a digital thread. There are also things in this diagram that don't exist. So if you look at this link right here, in my opinion, that link is really brittle and doesn't exist. There are things you can force it to exist, but when you really think about making the electrons or the blood or other things flow through this, between design and build, we need to know a lot more things. It wasn't until 4 or 5 years into our business that I ever thought about nominal CAD and thinking about then as built, as printed, as then subtracted, then as assembled, and then as ruined by the customer. But those are all the states that you need to plan for when you're looking at this digital thread. And the tools are just not that good. And I'll use specific examples. When we print an ollie, we simulate the ollie. But we have been working, and most of our patent development and work that we do at the company is on making that digital manufacturing work the same way every time. And so we've known that if we don't know how it's going to work, how does somebody else know how it's going to work? So where we are today between design and build, when we're thinking about as built, as cut, as assembled, and as ruined by the customer, this is what we want to know that we've simulated so that back at the CAD, we have a machine, a software that can tell us, hey, don't make that wall there. Don't put that soffit there. Don't put that radius there. Those are the things we want the computer to tell us so that we don't make those design mistakes, because our factory can build it very quickly. So we're missing some pieces in between, but we're getting there. So one of the things that you can see is this is a traditional ollie, and we took the time to build one in this way so that we would know the difference between printing it and making it out of a traditional frame or stamped body. And we can see the difference in assembly time and the difference in failure and the difference in weight and all of the other parameters that you need to solve for. And now we've come to a stage where we're beginning to add some of those sinews between those pieces of the digital thread. And then this is the latest printer that's being installed today, right now. This printer's 40 feet long. The chemistry isn't there for us to be able to print a submarine, but the will is there for us to be able to print a submarine. And if you went back to our first print in 2014, it took us 44 hours to print a vehicle that delaminated every third print. Today, we never delaminate, never when we print, because we understand the conditions and we understand the chemistry and we understand the setup and we understand the software to be able to make all those things come together and work. So we felt we had the guts to build a machine like this that could do multiple ollies at the same time in the machine. This machine will go live in 2 weeks and will be in production for this type of vehicle. This ollie shows roughly 2 times the torsional rigidity of a traditional vehicle. It has better crash properties, and it definitely holds way better equipment than the first vehicles that we would have made. And every time we want to make a change, we simply change the CAD at the digital thread, and we go back, and we now know much more about it. So this is it being printed. And then this is it being milled, pictures that you know about. But when we used to throw beads and we used to not understand what would happen, just to give you a sense, we used to spend 44 hours printing a vehicle and about as much time subtracting a vehicle. Today we print an ollie in 9 hours. And we spend 10% of that time doing subtractive work because of the way that things have moved along. But the design rules are still too analog. And so my call to industry is to try to get that moved along faster, so that we can get that predictive analysis up front for the CAD that you design, for all of the things that are going to come downstream, not just in additive and subtractive, but also when you assemble and validate. So this is an example of assembly from a torsion testing model where we're carefully controlling for all of the items that are going on in the vehicle, so we can validate our model and understand that it's not actually a suspension setup right there, but that's controlled for 6 degrees of freedom around the vehicle, so that we can actually torse the vehicle and understand whether the model is correct. And then lastly, of course, for us today is deploy and learn. So we've delivered vehicles now all over the world, literally. They're going to Australia, they're going to Korea, they're going to Copenhagen, they're going to several places in the United States, and it is happening right now. And it's super exciting to think about the fact that the microfactory soon will be able to follow the vehicles. So they can go to Copenhagen, and they can go to Australia, and they can go to Korea, and if we don't like the way the vehicle's working, we can send new instructions, we can take back in the vehicles, we can use those components that are still able to be used, like a new battery, new headlights, other things like that, and yet we can take back in the material, recycle it, and get a new design out that behaves better for what we're doing. So, my final comments here are that a mobility revolt is happening. It's all around us. It started for me in 2005 in Iraq, but basically the people and the places and the paradigms we think about it are evolving and revolving today in a way they haven't in 120 years. It's all around us, and it's not just Uber, and it's not just scooters, and it's not just bike sharing, it's everything. It's drones, it's all of those things. So we have an obligation to be great. Specifically, scientists, engineers, product designers, we have an obligation to dig in and be great. And we need to think about what happens when you poke the biggest system of them all, because mobility is definitely the biggest system of them all. In the US alone last year, we drove 3 trillion vehicle miles. That's not people miles, that's vehicle miles. And in the world, we drove 10 trillion miles. 10 trillion vehicle miles. If you cost that at $1 a mile, which is roughly what it costs to sustain vehicle mobility, that's a $10 trillion cost injury. How much will you pay for that industry? Depends on whether you're paying for it as a consumer or as the government. So, it's our job not to have that industry look like that picture behind. And not only that, that's just at end of life. You want your mobility devices to shine, not cause accidents, and not sit idle 95% of the time in your garage at work or your garage at home. Because all those do is they use resources, and they also hammer down on safety for people who are in the middle class and are up and coming and want a better quality of life. So that's what we started with in 2004 and 2005. And thanks to our partners at Siemens and so many other partners, we're here today at the cusp of being able to solve so many issues in a digital revolution, in a mobility revolution that's powered by a digital manufacturing capability. And I am thrilled to think about what next year will look like as we pursue new opportunities in the air, on the ground, and in the sea from microfactories that we're distributing. We have 3 microfactories now, and we're looking to put 5 more up in the next 3 years. And it's up to our community and this amazing group of technologists and supply chain partners to help us see the future sooner rather than later. So thank you so much for sharing the time today.